All right. Note an aromatic molecule is especially stable. Benzene is an aromatic molecule. It's a very stable molecule. Aromaticity makes things very stable. When you have an aromatic molecule, what that means is all of the pi electrons, the electrons in unhybridized p orbitals, if you're going that route, all of the pi symmetry electrons are delocalized. They are free to roam the molecule. Recall from the last video with benzene, where we kind of drew it like this, where we had the extreme of delocalization. There's all bonds are the exact same length. They're all a bond and a half. This is different than conjugation. Recall when you had a conjugated diene, you had a short bond, a longer bond, and a short bond, but the long bond, the single bond, was a little bit shorter than it should have been for a normal single bond. Not with an aromatic system. These 6 electrons, 1, 2, 3, 4, 5, 6, completely aromatic. They're completely free to roam the entire molecule. It's completely aromatic, and that's why we draw the circle, and that means very stable molecule. Electrons completely delocalized throughout the pi system. Let's look now at what might cause, or by looking at a molecule, if we can tell if it's going to have completely delocalized electrons. And there's 4 rules. First of all, it must be cyclic. It must start and then end back where it started from, or at least a part of the molecule must be cyclic. You must have a cyclic part to that molecule. That cyclic part must be planar. If you were to build the model, you would find out it's completely flat. Get your molecular models, build a molecular model of benzene, you'll find out it's a completely flat molecule. On the exam, however, you will not have your models. You cannot build it to see if it's completely flat or not. Therefore, rule number 2, we're just going to have to kind of say, yeah, we're going to have to just assume that if it meets all the other 3 rules, then it is going to be completely flat, because that is a situation. If rules 1, 3, and 4 are met, we know rule 2 is met. It's completely planar. Cyclic, yeah, see that planar? We're not going to know unless we build it, so let's just not worry about that. 3 must be completely conjugated. Now, there's an easy way to tell in some molecules about completely conjugated, but it only gets us halfway there. If you see it has alternating double and single bonds, so as you go around the ring, you can say single, double, single, double, single, double, single, double. So you can just keep going, single, double, yeah. Then it is completely conjugated. For our main molecule that we're dealing with most time, benzene, note, whoop, there it is, drawn right there. We can start here. It's okay, single, double, single, double, single, double, single, double, single, double, single, double. We never said 2 singles in a row. We never said 2 doubles in a row. Therefore, this is completely conjugated. As we go around the ring is completely conjugated. Now, if you see that, that's the easiest way to tell about complete conjugation. However, there are others, and these are what are going to trip you up. They're a little tricky. The truth of the matter is, to be completely conjugated just means every atom in the ring must have an unhybridized p orbital on it. Every atom in your cyclic part of your molecule must have an unhybridized p orbital. And double bonds is a way to get unhybridized p orbitals, but triple bonds can give you unhybridized p orbitals. There are other ways. Recall, carbocations have unhybridized p orbitals with no electrons in it. Carbanions are trigonoplanar. They have an unhybridized p orbital with 2 electrons in it. So watch out for this completely conjugated. Just because you do not see completely alternating double single bonds does not mean that it's not completely conjugated. Look for crazy situations. And the last rule is Huckel's rule. The ring must contain 4n plus 2 pi electrons, where n, I guess it could be 0, but really n equals 1, 2, 3, 4, 5, 6, 7, counting an integer. It can't be 2.5. It can't be 1.5. It has to be 1 or 2 or 3 or 4 or 5, the whole number here. If we look at benzene, if we just draw the structure for benzene, we can say, okay, there's one pi bond, another pi bond, three pi bonds. Each pi bond has 2 electrons in it, so that's 1, 2, 3, 4, 5, 6 pi electrons. If you have 6 pi electrons, does that satisfy Huckel's rule? Can 4 times some number n plus 2 equals 6? Well, very easy math. Says I can solve the equation if this is n here. 4 times 1 is 4 plus 2 is 6. 6 equals 6, yeah. Or I could just have put in my n here if you really need to go through this math. 4 times n plus 2 equals 6. How do you solve this equation? Oh, I don't know. Perhaps subtract 2 from each side. So 4 times n equals, well, what's 6 minus 2? 4. N equals 1. Yeah, okay, that was easy math. All right, so it satisfies Huckel's rule because you got an n value of 1 here. So it is aromatic. Hey, let's look at this molecule, cyclooctatetraene, a very nice molecule that explodes when in contact with air. Let's see if it is aromatic or not. Is it cyclic? Yes, it is cyclic. Is it planar? I have no idea unless I build it, and I can't have my models on the exam, so I don't know. Let's look at the others. Is it completely conjugated, alternating pi in single bonds? Single bond, double bond, single bond, double bond, single bond, double bond. Whoop, excuse me. Single bond, double bond, 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 single bond. Oh, yes, it is completely conjugated. Boom, don't know. Boom. 4. Does it follow Huckel's rule? Well, let's see. 4n plus 2 equals 8, because I've got 1, 2, 3, 4, 5, 6, 7, 8. 4n plus 2 equals 8. 4n equals 6. N equals 1.5. Is 1.5 an allowed number? No. It's got to be 1 or 2 or 3. So this is not aromatic. It does not follow Huckel's rule. This is not an aromatic compound. In fact, if you get your molecular models and build it, you will find when you put it together, it's not even planar. This molecule literally has 4 short carbon-carbon pi bonds, double bonds. It has 4 short double bonds and 4 long single bonds. There is no aromatic. There's no delocalization of the electrons. It's not planar. It is not aromatic. Okay. Occasionally, it is rare, occasionally you'll get a molecule that satisfies 1, 2, and 3. It's cyclic, it's planar, and it is completely conjugated. However, it does not follow Huckel's rule. If it isn't following Huckel's rule, but is completely conjugated and planar, there must be some other force holding it into its planar shape. And that force is going to, usually it's due to structure, or the limited number of carbon atoms. That is an anti-aromatic compound, and it is really unstable. A prime example is this one right here. What would we call that? Well, there's 4, so it's a cyclobutane, but there's 2 double bonds, so dicyclobutane. Okay, it's 1, 2, 3, 1, 3, dicyclobutene, dibutene. Yeah, okay. If you look at this, is it cyclic? Well, yes. Is it completely conjugated? Okay, double, single, double, single, double, single. Yeah, all right. Is it planar? If you build it, you find out it's planar. There's only 4 carbons in the ring. It is definitely, it is planar. Does it follow Huckel's rule? No. 4n plus 2 equals 4, n equals 0.5. It does not follow Huckel's rule. This is an anti-aromatic. It is extremely unstable, extremely reactive molecule. Okay. So, we will finish out this video. It's going to take us a little bit. You're not out of the woods yet. By going through some examples here. Let's look at this guy right here. The single ring molecule right here. Is this thing aromatic? Well, cyclic, yes. Planar, no idea. Completely conjugated, okay. Double single, double single, double single, double single, double single, double single. Yeah, completely conjugated. This is 14 annuline. Does it follow Huckel's rule? Well, 4n plus 2 equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 4n2 equals 14. 4n equals 12. N equals 3. Yeah, that's a whole number. That will work. This is an aromatic compound, which meant if you built this molecule, it would be flat. What about this one down here? Drawing's a little dorked up, but yeah, we got cyclic, yeah, planar, don't know. Double single, 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 double single. Okay, it is, yeah, looks good so far. Does it follow Huckel's rule? Well, 4n plus 2 equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 4n2 equals 16. 4n equals 14. No. N equals 3.5. Does not follow Huckel's rule, so it is not aromatic. It is not aromatic. If you built it, there's nothing holding it to be planar, so it's not anti-aromatic. It's just not a non-planar, non-aromatic molecule. This has individual double bonds and individual single bonds. All right. Look at this. If you have greater than one ring, naphthalene, it is aromatic. We've got this part is aromatic. The whole thing is aromatic. Anthracene, there are many ways going through this molecule to satisfy Huckel's rule. This whole thing turns out is flat. The whole thing is aromatic. Heterocycles, well, that's where fun comes up. Let's take what looks like a benzene ring, but put a nitrogen in for one of the carbons. This is pyridine. Note, pyridine has a lone pair on this nitrogen, but you can see it's got a double bond. We've got at least one double bond, so we know that this nitrogen is trigonal planar. And being trigonal planar, that means it is sp2 hybridized. Tells us this lone pair, since we already got a double bond here between an unhybridized p on the nitrogen and an unhybridized p on this carbon, this lone pair is in an sp2 hybrid orbital. But we've got double single, double single, double single, completely conjugated. It's cyclic. Turns out if you make it, it's flat. 1, 2, 3, 4, 5, 6 electrons in the pi system, in pi orbitals, and that follows Huckel's rule. So yes, this is an aromatic molecule because this lone pair is in an sp2 hybrid orbital, not in the unhybridized p. Well, let's look at this molecule, perol. Nitrogen, okay, 5-membered ring. Well, it's cyclic. Is it planar? Don't know. Is it completely conjugated? Well, that's a good question. Okay, I've got like double, single, single. Oh no. Let's look at this nitrogen. If you were to do the Lewis structure following your Gen Chem 1 rules, you would say that nitrogen, following the normal rules, that nitrogen you would label as sp3 hybridized. Because what do we have coming off of it? We've got a single bond, a single bond, a single bond, and a lone pair. Recall, that is a nitrogen with a single bond coming out at us, single bond back, and a lone pair. Yeah, that is 4 electron groups coming off that nitrogen. We'd expect that to be trigonal pyramidal. We'd expect that to be an sp3 hybridized nitrogen, and therefore no, because then it'd be double bond, single bond, double bond, single bond, single bond, not aromatic. However, what if this nitrogen said, hey, wait a minute here. I look like this. I'm looking at this kind of trigonal pyramidal structure. How much energy would it take for me to just go trigonal planar and put that lone pair in an unhybridized P? The answer is, well, it turns out it doesn't take much energy at all. So that's what it does. It turns out that this nitrogen is trigonal planar. It turns out that this nitrogen is sp2 hybridized with the lone pair in an unhybridized p orbital. Because when it does that, when this lone pair, if it's in an unhybridized p orbital, that means that all of a sudden you've got an sp2, 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 sp2. All 5 atoms of the ring are sp2 hybridized, which means it is completely conjugated. And if both electrons are in the unhybridized p orbital, that means I've got 1, 2, 3, 4, 5, 6 electrons in unhybridized p orbitals in the pi system. This is aromatic. So the structure of parole is going to break from our rules of Gen Chem 1 because of our new rules of Organic 2. If an atom, by becoming sp2 hybridized instead of sp3, if in doing so can be make it the molecule aromatic, it will do so because that's so much lower in energy. It's a much more stable molecule if it's aromatic. So note, with parole, this lone pair is in an unhybridized p orbital, which makes this aromatic. This lone pair for pyridine is in an sp2 hybrid. It's not in an unhybridized p. Why not? Why wouldn't pyridine put these 2 electrons in an unhybridized p orbital? Because if it did, that'd be 8 electrons in unhybridized p orbitals, 8 electrons in the pi system, and it would no longer be aromatic. Pyridine keeps these 2 electrons out of the pi system to ensure that it's aromatic. Parole puts those 2 electrons into the pi system to be sure that it is aromatic. What about furan? What do you think? From the get-go, we've seen oxygens with 2 bonds and 2 lone pairs, such as water, sp3 hybridized. At first glance, we would say, okay, not aromatic. But then we start to think, but wait a minute, is there any way to make this oxygen sp2 hybridized and make this aromatic? Well, note, if we made that oxygen sp2 hybridized, if it is an sp2 hybridized oxygen, that means we've got the single bond here. We could have 1 lone pair in the 3rd sp2 hybrid orbital, and that fills up the sp2 hybrid orbitals, 1, 2, and 3, which means this lone pair could be in the unhybridized p. And if this lone pair is in the unhybridized p right here, then I've got 1, 2, 3, 4, 5, 6 electrons in pi orbitals. It's cyclic, it's conjugated, sp2, 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 then it is aromatic. Yes, furan is aromatic because it is lower in energy for this oxygen to be sp2 hybridized and 1 lone pair in an unhybridized p to make it aromatic, much lower in energy than this oxygen being sp3 hybridized and non-aromatic. And there are some ions here. There are 2 famous examples of aromatic ions. One is a cyclopentadienyl anion. If you have this 5-membered ring, cyclopentadiene, let me just draw it out here for you to show you that with 2 hydrogens right here, this is double bond, single bond, double bond, single bond, single bond. This is not cyclopentadiene is not aromatic. However, you can have a base come in here and snag one of these protons, and then this bonding pair becomes a lone pair on that carbon, and you get this beast right here. Well, this is a carbanion, and we know carbanions are sp2 hybridized carbons with that lone pair in the unhybridized p. And we've seen this before. 5-membered ring, 2 double bonds, an atom that is sp2 with a lone pair in the unhybridized p, a la parole, means this is now aromatic. So these 2 electrons here from the lone pair on the in the unhybridized p orbital of this carbon And these pi electrons here are free to roam around the molecule, as is the same thing here. These four pi bonding electrons and the two lone pairs are roaming around all over the place. It's aromatic, as these guys are aromatic. So this cyclopentadienyl anion is very stable and is aromatics. And because things like to be aromatic, it's so stable, it turns out the pKa of these two protons is 15. Sodium hydroxide would do an excellent job of just coming in here and snagging that proton because the pKa is 15 because the product is so stable. And then another molecule that, truthfully, I have not looked up to see what good things this molecule can do. The thing I most often see it for is to mess up students on Organic 2 exams. Is this molecule aromatic? Whew, okay. It is cyclic. Yes, it is planar. I don't know. Is it completely conjugated? Well, we got double, single, double, single, double, single, single. So it's looking like it's not, but I see trickiness here. I see a carbocation. And what do I know about a carbocation? Oh, that's right. Carbocations are sp2 hybridized, which means this positive charge here is actually in an unhybridized p orbital, but it is trigonoplanar sp2 hybridized. How many electrons in the pi system? Well, none here. 1, 2, 3, 4, 5, 6. Note I've got 6 electrons. 4n plus 2 equals 6, n equals 1. So it follows Huckel's rule. sp2, 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 sp2. It's completely conjugated because each carbon is an sp2 hybridized carbon in that cycle. This, yes, this is an aromatic molecule. It's an aromatic ion. And the only time I've ever seen it is on exams to try to make sure you know the rules. All right. And that's it for this chapter. I told you it's a fairly short chapter. We will continue on next time with the reactions of aromatic compounds.